In this class, we are going to discuss about the three-phase half-wave control rectifier with resistive load. This is a circuit diagram. This is phase A voltage, phase B voltage, phase C voltage. These are the positive directional source currents SCR1, SCR2, SCR3. This point and neutral, we are connected the load. Suppose if the T1 is on, remaining two devices are off. The T1 is on, A is connected to the load. Nothing but load voltage is equal to the phase A voltage. Suppose if the T2 is conducting, remaining two devices are off. Now the B phase is connected to the load. Nothing but a load voltage becomes a B phase. Same manner, if the T3 is conducting, remaining two devices are off. Now the load voltage becomes a C phase. So we have to draw the load voltage waveform and load current waveform only when if we know the source voltage waveform. Here we have taken the three-phase voltage VA equal to Vm sin omega t, VB equal to Vm sin omega t minus 120 degrees, Vc equal to Vm sin omega t minus 240 degrees. The three voltages are mutually displaced by 120 degrees. We have taken the input voltage as a phase voltage because when the SCR is conducting, load is getting the phase voltage only. Whenever these SCRs are forward bias means input voltage of SCR is maintained more positive than the remaining two phases. From that point, the particular device will be forward bias. Now we are going to take the three phase voltages 0 degree, 60 degree, 120, 180, 240, 300, 360. We have taken the scale. First we have drawn the phase A voltage which is starting point is 0 degree. Next phase B voltage, the starting point for the phase B is 120 degrees. Phase C, the starting point for the phase C is the 240 degrees. This is phase A voltage, this is phase B voltage, this is the phase C voltage. From 30 degrees to 150 degrees, phase A maintains the more positive voltage compared to the remaining two phases. So, in this duration, SCR1 is forward bias. So, whatever the firing pulse we are applying to the SCR1, that we have measured from this point is nothing but a knee point. Again from 150 to 270, phase B maintains the more positive. In phase B, second device is there, so it is forward bias from this point. So whatever the firing pulse we are applying to T2, that we are measured from this point. The similar manner, third SCR will be forward bias from 270 degrees onwards. Here we have taken the firing angle alpha equal to 30 degrees. So the T1 will be on at a 60 degrees. At this point the T1 is on because whatever the firing pulse we are applying to the T1, that we have measured from this point. T1 is on at a 60 degrees. From this point the T1 is on. Once the T1 is on, it has to conduct a 120 degrees, nothing but up to 180 degrees it is conducting. At 180 degrees the T1 will be off and next device T2 will be conducting. Here T2 is conducting. Again 120 degrees it is conducting up to 300. So here 60 degrees and starting 60 degrees T3 has to conduct. For a firing angle alpha equal to 30 degrees. If you draw the output voltage waveform, at this point the T1 is on. Once the T1 is on, the output voltage is equal to the source voltage phase A. This is phase A. So from this point you have to see how the input voltage is changing up to 180 degrees. You take up the same magnitude, the same waveform. This is the phase A voltage. And at this point T2 is conducting. Once the T2 is conducting, the output voltage follows the input voltage of T2, that is phase B. So from this point you have to see how the phase B is changing. You take up the same magnitude and same waveform up to here. At this point, nothing but 300 degrees, T2 will be off and T3 will be on. So once the T3 is on, the output voltage follows the input voltage T3, that is Vc. So from this point you will see how the Vc is changing. We complete the output voltage waveform. Now we are going to draw the output current waveform. Here load is a resistive load, so this voltage waveform divided by the resistance that gives the current waveform. The current waveform is same as the voltage waveform, but the magnitude will be lesser. You have taken the R value is greater than the 1. This is phase A, this is phase B, this is phase C. Next we are going to draw the phase A current. From 0 to 60 degrees, this current is supplied by the phase C. So the phase A current becomes a 0. Now phase A is supplying a current from 60 to 180 degrees. You take up the same magnitude and same waveform. The remaining durations, the phase A is not supplying any current. So you have to take the phase A current becomes a 0. The same manner, you have to draw the phase B current. Phase B is supplying a current here in this duration. The remaining duration, phase B current becomes a 0. Same manner you have to draw for the phase C. To find the average output voltage from 60 degrees to 180 degrees, this is the waveform which is repeating. The base length becomes a 180 minus 60, that becomes a 120 degrees. Now we have to find out the area under this curve. Here, this point we can write it as a pi by 6 plus alpha, and this point we can write it as a 5 pi by 6 plus alpha. Now we are going to keep the same circuit operation in the table form. 60 to 180 degrees, T1 is conducting, the output voltage becomes a VA. 180 to 300 degrees, T2 is conducting, output voltage becomes a VB. 300 to 360 degrees, T3 is conducting, the output voltage becomes a VC. Now we have to find out the average output voltage. The base length of a repeated waveform becomes a 2 pi by 3. So 1 by base length. So here you are getting the 3 by 2 pi. Integral pi by 6 plus alpha to 5 pi by 6 plus alpha. Vm sin omega t d omega t. This is nothing but a phase A voltage. Now we complete this integration. We are getting the 3 Vm by 2 pi cos of pi by 6 plus alpha minus cos of 5 pi by 6 plus alpha. This is in cos C minus cos D formula. Use this formula and reduce this one. Finally, you are getting the 3 root 3 Vm by 4 pi into cos of alpha. This is the average output voltage given by the 3-phase half-wave control rectifier circuit with a resistive load. The firing angle less than the 30 degrees. Thank you very much for watching this video.